This material is made available to you by or on behalf of the University of Melbourne under Section 113P of the Copyright Act 1968. It may be subject to copyright. For more information, visit the University Copyright website.
And what, to a degree, a generic response we get without going into a specific application. So as usual, I've listed what textbooks, what chapters I've gone from the textbook. However, with this one, so here if you've already had a look at the notes, I cover a bit about non-fouling, how to modify surfaces, how our body changes or how our body can change the materials, sticking with mainly hydrolysis and polymers. What I've done is kind of summarised some what I consider as important concepts. So I used to give a lecture on polymer hydrolysis that went for 3 hours on that alone, and I've kind of summarised it into 10 slides. So while I've got all of the different sections, like with some of the other ones, I'm not expecting you to go and learn all 4 chapters because that is a lot. However, the bits that I touch on, this is where I got the information from. So if you wanted it in a little bit more detail, that is where it is. And the concepts that I'll go over in the lecture is what I may ask an exam question on. So by me putting this up here and I don't cover it in the lecture, don't expect me to ask an exam question. I'm not saying, because I guess that's where the classes where it's learn this from the textbook and then we'll go over in there. This here I am saying is a lot of content. So I don't expect you to learn all 4, but these are the main points that I wanted to get across. I've got this picture like I usually do, or for what I have for the other past ones. We've got the local interactions, systemic interactions, and then how the device plays a role in that. And so what we will go to today is if we modify a surface, how that may change host response. And what do I mean by that? You've had a lecture on metals, polymers. So these materials may have some of the properties that you want, but then they may not interact biologically the same. So rather than changing a whole new material, because then that could mean a whole range of different properties that you'll get by changing that, can you make a small change to the surface to change how the material interacts? And then the other one is, if we implant a material into the body, what does the host do to it? So in some of the other lectures, I've touched upon different enzymes. So enzymes may affect the material, they may break it down. Our body is pretty much water. And particularly for polymers, if there are particular polymers that are in your material, will water affect it? So in a lot of the other lectures, I've kind of harped on about if a material is going to interact with the body, it has to do with, or a lot of it has to do with proteins absorbing onto the surface. So a lot of materials, you may hear or refer to them as a non-fouling surface. So a non-fouling surfaces are surfaces that essentially resist absorption of proteins and or cells, depending on what you're looking at. So has anybody heard of PEG before? Did you go through a little bit about PEG in the polymers material? So PEG is polyethylene glycol. I'm also trying not to go too in-depth into the chemistry, more about what properties of those materials are relevant. But one of the most commonly referred to non-fouling material is PEG. So polyethylene glycol, and that's the chemical structure. So like with all polymers, a polymer is a repeating chain of something, poly, many, mer, unit. And it's here, this N, to, like with a lot of other polymers, what that N is or what number it is and how big the polymer is can change a lot of the properties. And I guess while I say it's commonly referred to as PEG, sometimes you might see it as PEG, sometimes it might be in a textbook as polyethylene oxide, and sometimes it might even be there as oligoethylene oxide. Sorry, oligoethylene glycol. And really, these three, It's all the same chemical repeating structure. I don't want to say it's all the same properties, because if you change the molecular weight, you are going to change the properties of the material. But it's all that same repeating unit. So if you look in the textbook about non-fouling surfaces, it gives you this definition. The resistance to protein absorption at the biomaterial interface is directly related to the interfacial groups to the release of their bound waters of hydration. What does that all mean? Have you guys done thermodynamics? So there's, the textbook goes into all of these different properties about how, well, not different properties, but how thermodynamics plays a role in this. To summarize that statement into what affects, or one of the big things about whether or not a material is anti-fouling or not, it's really, do surfaces like water or not? So the hydrophilicity property, hydrophilic, I'm not going to say it right. So properties of a surface, whether or not water likes it or water doesn't. Hydrophobic is a water liking or water hating surface. Phobia, doesn't like water. Hydrophilic, likes water. So sometimes, and I think I've referred to in some of the other slides, in general, a hydrophilic surface won't absorb proteins. If a surface won't absorb proteins, then cells in general don't like to adhere to it. I will always say in general, because you will always find there is a material that that rule does not apply to. So I don't tend to like taking pictures from the textbook, but this is one that I thought summarised surface modification very nicely. I don't really expect you to know what each one of these means and how to modify surface by each one of these. The general gist or the take-home message that I want you from this one is that if you have a particular material, so take for an instance a metal. You might use a metal in a hip implant. Depending on that surface of the metal, it may interact with the body that is not just, it may have a non-desired interaction. You're not going to want to shove a polymer in a hip. You can get hard polymers, but because of the amount of load that goes onto a hip, is it going to be as strong or have the same mechanical properties as a metal? Possibly not. Can you do something to the surface? So a lot of things with surface modification is that, in general, it's not limited to one type of material. You can probably do it on a whole range of things. So if you have your unmodified surface, you can put a surface coating on the top of it. So something like that is dip coating. So quite often you'll get, I was trying to come up with an example. Have you ever had a piece of metal and it has a bit of, like it has a polymer, plastic around it? So that's dip coating. You get your device, you put it in a liquid, could be a polymer, you dip it in, you dip it out, it's a coated surface. A very easy way to change then the properties of what our body sees of that material. Then you have a surface gradient, so then that's integrating two different materials together. It's different to an overcoat or surface coating. You then can, things that can affect it is this layer in the middle here, how well they bond to each other. You can have a self-assembled monolayer or self-assembled layer. You can graft something onto the surface. You can add things to the bulk of your material that, depending on how it changes, will come to the top. A surface chemical reaction, so that's modifying chemically the surface. I've got etching and roughening, so surface patterning. You can change the topography of the surface. So that is something that is quite often done with metals, is changing the surface roughness. And then there's also the polyultralight multi-layer films. So within the textbook, when it gives you each of these examples, it goes into a little bit more detail about what these examples are. So the next couple of slides are examples of literature that has done this. So a metal, depending on what application it's used for, typically smooth. So what this study did is look at a smooth surface, a rough surface, but then also change the surface properties chemically. So they had smooth, rough, and then hydrophilic. So has anybody seen an image like this before? So that's called contact. It's looking at contact angle. What that essentially is you get a drop of water, you drop it onto the surface of your material, you quickly take a picture with a high-speed camera so it gets it as soon as it's on there, and then you look at, it's going to be that angle there. No, that's not right, because if that's 120, I have to go and look that up. You look at it, the angle that the water or the water droplet then sits on the surface. So something that's hydrophilic, something that likes water, the water as soon as it drops on it is just going to go straight, flat. So a surface that is hydrophilic is going to have a contact angle of less than 90 degrees. So the water has started to spread. If it's hydrophobic, it's going to be greater than 90 degrees. So that's a very simple method of measuring whether a surface is hydrophobic or hydrophilic. When you put water on it, does the water just spread out, or does you see a bubble form? So in this study, I don't have any nice pictures of cells on this, because within this study they were looking at host response, so inflammation and macrophages. So they didn't have any cells adhering onto the surface, but what they did was measure the expression of all these different chemokines and cytokines that you get from macrophages, and that tells you what sort of state it is in. And by what sort of state, what I mean by that is, and what I didn't go through when I was talking about inflammation, some people say macrophages are good and help inflammation, so pro-inflammatory, and some people will say that macrophages are anti-inflammatory. So sometimes they help inflammation and sometimes they make inflammation work. And that depends on what type of macrophage it is. And you can tell what type of macrophage it is by looking at their gene expression. So here, they isolated a population of macrophages that had come into contact with these materials and looked at what genes were expressed. And this really just summarised what they could show without showing you the results, because it's just a whole lot of bar graphs with different cytokines. But they were able to show that, so something that was rough and then also hydrophilic polarised the immune response to a pro-wound healing phenotype of macrophages. And that was able to promote stem cell recruitment and tissue regeneration. So they were able to find that by not only making the surface rough, but then changing the chemistry of the material, so that or chemistry of the surface, so you had something that was more hydrophilic than hydrophobic, you were able to modulate the immune response to the materials. So you were able to make it more pro-inflammatory and to recruit in more cells that are going to help the wound healing process, rather than recruiting inflammatory cells that are going to make it have more of an inflammatory response and have more of the bad inflammatory cells that come in. So you're creating a surface that helps, in a way, tissues heal and tissues remodel. So the other thing that they did, well, this is more just showing the chemical composition. So I think this is what they've used. It's something that's quite used often, is a technique called XPS. I don't remember the acronym, what it stands for off the top of my head, but what it is a technique that shines a beam into the material. It creates a beam shines into the material, it gets refracted off it, or different excitation wavelengths get emitted, and then you can work out what the chemical composition is from that. I'm not going to go into the theory of how that works because I know I will say it wrong, but it's a technique that you're able to do elemental analysis of a surface. So by that, they looked at nitrogen, carbon, oxygen, and titanium. So the main elements that you would find in this type of metal. The main thing that they saw was the change in oxygen. So because this is all a percentage, it's a percentage of the total surface composition, it all has to add up to 100. So if you get a big change in one number, the other numbers are going to change, but they don't change very much. But you see a whole lot of oxygen. And by what they're applying is the change in oxygen, or the amount of oxygen component in there, is going to have an effect on the hydrophilic properties of the materials. So that's just one example of, particularly for a metal, how you can change the surface properties, either topography or chemistry, to change how the body responds to it. So the other thing is, or another example is surface patterning. So this is just one type of surface patterning. Another one of the common applications the surface patterning is used for is microfluidics. Do you guys do fluid mechanics? Microfluidics is a technique that's commonly used for things like biosensors. So it's microfluidics. You can make fluid devices that are, I've seen pictures of them, they're the same size as like a $2 coin. So they're tiny microfluidic devices that by controlling the geometry, you can control the flow of the fluid in there, and you can simulate biological experiments, something that's the size of $2 coin. So quite often things will be called like a lab on a chip, and that's where microfluidic comes in. So you can grow particular cells and on there and simulate different organs or different biological environments. But that's kind of going off topic because I think you may do a little bit, if you take the tissue engineering subject, they may go into that in a little bit more detail. But it's one example of surface patterning. So here is an example of surface patterning where they've changed one property, kept another property the same, and looked at when you put platelets onto those surfaces, whether or not it changes platelet adhesion. So by keeping the chemistry the same, and what have they kept? So it's the same aspect ratio, so the same width to height of these little pillars. So if you were to look at the surface front on, you would see something like this. So they've kept the width to the height, and then they've changed the distance. By changing one variable, so the chemistry is the same, nothing different to the chemistry. The width and the height are the same, but then they've changed how far away they are from each other. You can then change or modulate whether or not, or how you can modulate platelet adhesion to these materials. So one thing about materials, remember back to the picture that I showed on Wednesday, the biomaterial surface, and you had the platelets adhering on, and that's the same with cells as well. You had the surface, you had the different proteins on there, and then the platelets adhered through different integrins. So cells will adhere onto surfaces through integrins. If they're too far away from one bit to another, the cells aren't going to be able to attach on. If you have them close together, sometimes it can. So by changing some of these surface properties where bits of cells can adhere onto surfaces, you can then also modulate. So you're not changing the chemistry, but bits where cells can adhere on. And sometimes, depending on also the geometry, the shape and the height, cells don't like to wrap around it. So you can also change how cells, whether or not they will adhere onto there. Like with everything else that I keep on saying, is that the surface pattern for platelets, if you were to put another cell type on there, and so here, cells like to adhere onto this one. They don't like to as much onto this one. I should really do a tick or a cross. If I were to put a fibroblast onto this one, and then put it onto this one, I probably wouldn't see as much of a difference. And by what I mean by that is, the surface patterning that you have on here, and it changes the adhesion for one cell type, may not necessarily work for another cell type. So it's one of those things where just because it works for one, doesn't mean it works for another. But it is another example of how you can change a property of a surface to change how our body interacts with it. So this one is kind of combining both a chemistry aspect, but then also the biomolecules. So I think I've pretty much made it clear you can control whether or not a cell adheres onto a surface to whether or not there's particular proteins present. So if you have a surface that doesn't, it might be hydrophilic, and cells or proteins might not like to adhere onto it, but if you graft particular proteins of interest on there, can you then get specific cells to come and bind onto it? So I'll show you an example of that. So you've got proteins or even peptides. So peptides are short proteins, so you might have a particular sequence in a protein. They could be cell adhesion molecules, so proteins that promote cell adhesion, or they could be blocking molecules, so proteins that block cell adhesion. And in the slide that I had all of the different ways that you can modify the surface, you could attach proteins onto the surface by making multi-layers. You could do it by chemical reaction. You could do it by self-assembled layers. You could probably do it by other techniques as well, but for me these were probably the three main ones. One of the other things is, depending on which chemistry you choose, if you use a surface chemical reaction, you could be covalently attaching it onto the surface. And what I mean by covalent attachment, it then can't come off. If you put it on by usually the polyelectrolyte on there, it forms by ionic interaction. So they're by different charges. So while that is stable under some conditions, if you change the condition, your surface could come off. So a covalent attachment is pretty much permanent. It's hard chemistry to remove it off. So it's usually chemistry in our body, unless it's able to chemically cleave it, will stay on there. Whereas if you have a polyelectrolyte or a layer by layer surface, if you change the charge changes when you change pH. So if your pH changes in your body, could that change your surface? So I'm more emphasizing that there are different ways to put it on, but then also, are you wanting to put it onto the surface so it's permanent? Or by the technique that you choose, could it be not permanent and come off? So I've given some examples. I'll go through a literature example of proteins going onto, or surface modifying the surface with proteins. But here's just some examples of where you might surface modify, where you might chemically modify a surface to attach a particular biological molecule. So for an enzyme, you might put it into a bioreactor. You might have it on the surface of a bioreactor by sensors. So probably one of the experiments that I used to do with high school students used to come for open day, we developed a biosensor to show students how to, or to demonstrate how you might come up with a diagnostic for diabetes. So if a patient has diabetes, they have a lot of sugar in their urine because their body can't process it. That's one of the main indications. And we came up with a diagnostic where if you put an enzyme that chops up sugar, if it chops up sugar, it will change colour. So you could put a drop of a patient's urine with diabetes and without it onto this sensor, and because you had an enzyme tethered to it, it would either change colour or not. So that's a very simple diagnostic of something changes colour. You can put an enzyme onto a surface for a biosensor, and you can also use it as a diagnostic assay as well. So you could also tether drugs to the surface. So a lot of the thromboresistant applications will tether anticoagulants onto surface. Has anybody heard of heparin? So heparin is a well-known anticoagulant. Quite often people will try, in the literature, they'll try and make a surface, something that normally platelets would adhere to, put graft heparin onto the surface. So that's one example. And then you have drug delivery systems. I was going to give the example of a drug-eluting stent, but that is not something being grafted onto the surface. That's something being encapsulated and being released over time. So that is actually something that's different to grafting onto the surface. You could also graft cells onto the surface. So for things like bioreactors, if you're making recombinant proteins, cells make proteins, you can transfect them so that they make a particular product. And an example is also bioartificial organs and biosensors. So just quickly, well, not really just quickly, but you've seen these three before in the past 2 lectures this week. So fibronectin, vitronectin, and collagen. Platelets like to adhere to these, and they like to adhere to this one as well. And there's lots of different cell types that like to adhere to collagen. I'm not saying platelets, platelets also like to adhere to collagen. So people have actually found what sequence, what peptide sequence in that long protein the cells actually like to adhere to. And what it is, it's the integrin in the cells that actually like to bind to this. So within fibronectin, these peptide sequences, cells will bind to. In vitronectin, it's this one here, and in collagen 1, it's this one here. One thing that you will notice here, 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 you see RGD. So RGD is probably is the most common peptide sequence that we know and is used to turn something that cells don't like to adhere onto. You add that peptide sequence and cells do like to adhere onto it because it's in all of these different ECM proteins, and we know that cells like to adhere to these ECM proteins, and it's really the integrin of the different cell types interacts with this particular peptide sequence. So here is just a little schematic. I keep on talking about integrins, or I've mentioned it a few times, and when I had the picture of the platelets, there was the platelets and they were going onto the surface, and then you saw things coming down like this, and I think there was, you see things like, I don't know the exact number, alpha something, beta something. You don't need to know what those numbers refer to, but this here is the integrin, and that's what it binds to these particular sequences. So for example, here I have some collagen 1 on my surface of my material. So collagen 1 is going to have this particular peptide sequence in there. So one cell may have an integrin receptor that likes the DGEA sequence, so it will bind to the surface. Here is a different cell type that has an integrin that doesn't like it, so it won't. So that's one way by taking a particular peptide sequence, putting it onto your surface, and cells bind to it. The only thing you need to be careful about is what it is. So something like IgG, a whole range of cells like to adhere to it. So if you put it on there, you're not going to get a specific cell type. So this is an example of putting a peptide sequence on or incorporating it into a material. So this was a hydrogel. It's very similar chemistry to PEG, so it's known for being protein resistant. So if you have the hydrogel by itself, there's one tiny cell on there, but if you quantify it, so this is cell attachment, number of cells. Hydrogels, not very much. This here is an experimental control. So hydrogels are made by cross-linking. So this was the cross-linker that I used. Then I have the gel here with, it's not RGD, it's RDG. So that's by flipping the sequence of that peptide. You get a few cells that will grow on it. So that's this one here. There's a few, there's not that many. You put the RGD sequence in there, cells love it. So you can go from a material here, proteins don't like to adhere to it, cells don't like to adhere to it either. You keep the hydrogel material the same, you put in the sequence RGD that cells like to bind to, and cells all of a sudden love a material. So it's just an example of how you can change the properties without changing the chemical properties of your bulk material, change something small to another part of the material, and change completely how biology behaves towards it. So that is a very, very small snippet of how you can change the surface of a material to affect biological interaction, and was pretty much summarized only a few components of, I think, 3 chapters. So there are many other different ways, there are many other examples. But I also wanted to talk a little bit about, without running out of time like I usually do, degradation of materials in the body. So you implant a material into the body. Some materials you want to degrade and some of them you don't. So it can degrade chemically, and that's what I'm going to focus on. But you can also degrade macroscopically, so that's fatigue. So something like a heart valve that has a lot of mechanical repetition, it could degrade that way. Fatigue, you could get wear. So quite often with some of the old hip implants, you get wear between the different components and it starts to degrade, stuff comes off. And stress. So I'm not going to cover these 3 in this lecture now, because when I talk about particular applications, I'll go through more of an application specific ones of these. But we will quickly go through hydrolysis and enzymatic. So there is going to be a little bit of chemistry in here. I will tell you what bits I want to focus on, I want you to focus on, rather than some of it, I've just put it there to show as examples. So chemical degradation, it most commonly occurs with polymers. I'm not saying it's not going to occur with ceramics or metals, but it is most commonly associated with polymers. So what is chemical degradation? So it's the chemical changes of, I've kept polymeric material that result in changes in the properties of that material. Is it desired? Is it undesired? As always, it depends on the material and it depends on the application. So this just shows really what the difference of that is in a cartoon. So something that doesn't degrade, you want it to remain the same over time. Something that is degradable, it will change over time. So in terms of polymer degradation, and I've got here biodegradation, because here we're just focusing what happens in the body. You have an enzymatic, you have a hydrolysis, they're the main ones, but then you can have a combination of the 2. And then with hydrolysis, you can have bulk hydrolysis or surface hydrolysis. I also have put hidden in there thermal degradation. So I've put thermal degradation. We'll talk about it a little bit more when we go into industry applications, because While thermal degradation doesn't really happen in our body stays, unless, well, I guess if you get sick and your body temperature rises, you're more likely to have organ failure than failure of the material. But in terms of thermal degradation, how do we need to process the material to actually make a device? But then also, devices need to be sterilised. There are a few ways to sterilise a material. One of them is an autoclave. So an autoclave is high steam and high pressure. So if your material undergoes thermal degradation, you pretty much rule out autoclaving as a method to sterilise your material. This bit here is more for your interest rather than knowing what the chemical structure is. I don't expect that. This here is the, I guess in a way, the generic chemical reaction that occurs during hydrolysis. So hydrolysis, so it's succession of acceptable molecular groups by reaction with water. So depending on what group is there will depend on whether or not water reacts to it. This is the bit that I would like you to pay more attention to it. So what are different factors or properties of materials that will affect whether or not hydrolysis might occur? So hydrophobic. More hydrophobic it is, the less hydrolysis there is. If it's more hydrophobic, water doesn't like it, so water doesn't come near it. So if water doesn't come near it, hydrolysis is less likely to occur. Molecular weight. The higher the molecular weight, usually the bigger the polymer, the less likely hydrolysis is going to occur. Usually because if it's a particular chemical bond that the hydrolysis will break, there might be more of it to break before they're before you see a bigger change in the material properties as well. Then morphology, crystallinity. So that has to do with, if I say crystallinity, does that make sense or not really? So these are different properties of polymers. So how crystalline it is depends on what the glass transition temperature is. And that has to do with how freely the different polymer molecules move around at different temperatures. So if the glass, depending on where the glass transition temperature is, sometimes your polymer might be molten or liquid, sometimes it might be solid, and then if it's a solid, it might be crystalline or not. So then that has to do with macromolecular movement within the polymer. But really, if it's crystallinity reduces hydrolysis, porosity increases hydrolysis, so if it's more porous, more water can get in, and TG, depending on what it is, there's less mobility, so if things can't move around as much, you may get less hydrolysis. So here's some examples. So really more how hydrolysis can occur. It can occur at the surface of the material and work its way in, or it can occur as a bulk erosion. So it's this. Surface erosion occurs when mass loss is faster than the ingress of water. So ingress means water coming into the material, or you have bulk degradation. So this is where water goes in faster than the rate of degradation occurring. So you get something that looks like that. I'm pretty sure some of these polymers were mentioned when you did the polymer lecture. So in a way, it's hard to explain why this happens without going into the chemistry of the material, but these are all common polymers that are used in different medical devices. And really you have to know which one to use when you're looking at different applications, particularly if you're looking at a biodegradable material. Do you want it to degrade away at the surface, or do you want to degrade away at the bulk? Sometimes this can also be very important if you're designing something if you want something to degrade away. As it degrades away, do you want a drug to be released? So particularly that is important whether or not you choose something from a bulk, goes through bulk erosion, or surface erosion. So the other thing is enzymatic degradation. So I've listed here some common enzymes that you find in the body. So these are all hydrolases. So remember I thought before, or maybe it was the first lecture, I said if it ends with an A's, it may be, it's most likely to be an enzyme. Not all of these, the actual enzyme names ends with A's, this one does. Depending on what it is, it will have particular specificity for the substrate. So trypsin, have you done the cellular and tissue engineering subject? It's coming up maybe later, or you may not even choose it as an elective. If you grow cells on a surface, so when I do cell culture, I will grow cells on a surface. If I want to remove the cells off the surface, how do I do that? I usually put trypsin on them. So trypsin is an enzyme that will chop up bits around the surface of the cells so that the cells come up off the surface. And then all hydrolases have that chemical reaction. So all enzymes will work under their own set of optimal conditions. And within the body, most enzymes, their optimal conditions will depend on what pH it is, what temperature it is, I don't know why I've put enzyme there because it obviously depends on what the enzyme is to what the activity is, and then the substrate. And by the substrate I mean what is it actually chewing up. So for example, an enzyme in your stomach will have a different level of activity as compared to the enzyme in your lower intestine. They have different pHs. So that's one way, and really the enzyme still may work at a different pH, but it won't be optimal. So it may not work as fast. So the last few slides is another example that I'm going to show you about looking at how putting a material into our body changes material properties. Have we all heard of polyurethane before? So polyurethane is is in a way a nice polymer to work with. So polyurethane is made up of 3 different monomer components that you then polymerize together to make the actual polyurethane chain. Depending on what those 3 different monomer components are and the ratio of them, you can change the properties of the polyurethane dramatically. So these here are 4 different types of polyurethanes. These 2 have the exact same monomer components. They're equal, the ratios are different. So this one is very soft, and this one is very hard. So the chemistry is kind of the same. By changing the ratio, you change the properties, but it has the same chemical. This one here, so you know this 80, 80, 55D, 55D is a measure of hardness. So higher number, the softer it is, lower number, the harder it is. So the ones with 55Ds, they have, in terms of hardness of a material, so they are the same. and the same with the ADAs. So here, you're comparing hard versus soft, but the same chemistry. This one here and this one here, you're comparing the same softness, but then this one has different chemistry to this one. Here, this one has the same hardness, so the same, in a way, mechanical properties, but then different chemistry. So this is a very nice example of how you can change different material variables to change different material properties, and then we'll see how that actually affects its interaction when it's implanted. So this study was designed to look at long-term biostability studies. So all of these materials were implanted, and they were implanted into the back of the sheep, and they were explanted, some of them after 3 months, some of them stayed in there up to 24 months. The other nice thing about this study is, because they're polymers, you can punch it out with a die so you can get a particular shape that you want. You can then, with polymers, similar to what I said Wednesday about testing over the right period of time with blood. So if you're doing a study that lasts for 2 or 3 days on something that you want to implant for 2 or 3 years, you can't really extrapolate. With polymers, one thing that you can do with these ones is that you can stretch them to 150% elongation, and it's kind of speeding up. So this is one example of, you can do something to material to help, or to, you're doing a study even though it's between 3 and 24 months. You're doing something that can also speed up how the body might affect its interaction. So these were explanted. Then they did a whole range of studies that looked at chemical composition, how that changes within the body, morphology of the materials, and then also mechanical properties. So SEM images were taken to have a look at macroscopically the structure. So if I go 1, 2, 3, 4, in terms of biostability of these materials, most biostable means you can't really see very much of a difference, or it doesn't look like much has happened, and least biostable, there is a big difference, or that putting it into the body has really affected the material. Would you say 1, 2, 3, or 4? 1, 2, 3, 4? None of them? So this one here, by implanting, so if you have a polymer, I guess I'm not really showing you also images of what they look like to start with. Polymer is usually nice and flat. We're not changing the surfaces of we're not adding anything to the surface. We're just implanting a polymer film and seeing what the body does to it. Here, you can see all these cracks have started to form. You've got a great big hole in the material here. So this, to me, is saying that the material is starting to degrade in the body. So this one here, number 1, you might see a few little dots. There's like a scratch or two, and the same here. So something might have started it here onto there. But looking at 1, 2, and 3, after 3 months being implanted, not too much of a change, but whereas this one here, after 3 months, that has started to fall apart, or is starting to. So another test that they ran was GPC, so gel permeation chromatography. Can you tell from the axis what this is measuring, or a technique that uses to measure something? So if I'm measuring the molecular weight, I'm measuring the size of the polymer. If I'm looking at whether or not it's being degraded into in the body, the size of that polymer may get smaller. So by doing GPC analysis of the samples when they get expanded over time and looking what the molecular weight is, you can see if the molecular weight changes. If the molecular weight changes, something's obviously happening to the chemistry. So you're looking at 0 months, 3 months, 6 months, 9 months, 12 months. For all of the materials, you can see the line go like this. So for all of them, the molecular weight dropped over time. So for all of them, some sort of hydrolysis was going on. There was a whole lot of other tests to look at the chemistry of it as well and how much that changed, but I won't go into it. What was also quite interesting was looking at the mechanical properties of these materials. So for all of them, the purple is the unimplanted, and then the pink is the implanted. So you guys had a look at stress strain curves before? So these are in there for 12 months. So implanting these materials into the sheep for 12 months, then explaining them, explanting them, and then doing, I want to say Instron, but Instron is the name of the equipment, not the actual test. But the mechanical testing, so you put it in there and measure the stress and the strain. How much of a difference implanting these materials into the body changed it? They're all on the same scale, so they all go up to 800, but they don't have the same stress. So this one only goes up to 80, this one 200, this one 90. So it's a little bit harder to compare the graphs to one another. This was taken from the paper, I didn't graph it, but just between each of them you can see. So the other thing is, there's no P80A. So P80A was this one here. So that's after 3 months it looked like that. Can you hazard a guess to why there isn't one of these graphs for P80A? It did not last 12 months. They expanded it and all of them had already degraded so much that you couldn't mechanically test them. So that's just an example, looking at the different chemical properties of something, how much, or even not just how much materials change in how they behave, but when you implant them, what our body can do to them. This is something you've designed to behave one way, you put it in the body for 12 months, and you get completely different properties. So that is the end of the lecture. I put this. So I have a colleague who works in Sydney and she teaches biocompatibility. And her class asked her, is there anything we can do to get some extra marks? And it wasn't an actual assessment, but she was like, if you want to come up with a meme to describe biocompatibility, by all means. And she actually found that what the students were coming up with were very good at summing up different aspects of biocompatibility. So I'm probably too old to know who that person is, but anyway. So here, he's got which one to choose. Negatively charged surfaces repel platelets and negatively charged surfaces cause coagulation. There are studies that are going to show both. There will be studies that show if it's negatively charged, it repels platelets. And there'll be ones where it shows if they're negatively charged, it causes coagulation. If it's causing coagulation, what does that mean? It's not repelling platelets. So it's one of those things where this topic is so hard to say this is always what happens, because it will happen for one thing and it won't happen for another. One of the big things you need to know with biomaterials and testing them is that what tests to do and how to interpret, and really designing the tests to show, or designing the right tests to test the material for what you want to use it for. And so that's why the next couple of lectures will go through in detail more about the biological testing. But I just thought it was pretty, sums it up quite nicely. Which one do you choose? Because it both happens for both. So I've managed to finish a minute before 5:15. Have a very nice weekend. Remember on Tuesday, the lecture is not being recorded. You'll have a guest lecture. I will be there for that, and I will see you as well next Wednesday.
first paragraph. See, we might both go the same content.